A perfect square. If we start talking about if something is a perfect square, what you're going to write down is this. A rational number, if you think back, at some point you would have learned number sets, integers, rationals, irrationals, whole numbers, all that good stuff. A rational number is a non-fraction. So like 2, 6, the numbers that you see down here on the left-hand side of the table. So a rational number multiplied by itself. All right, so an example, simple little example. If I said 3 times 3 is a 9, the 9 is the perfect square because that's a rational number. 3 got multiplied by itself. It gave us a 9. So 9 is what we would call a perfect square. Okay. So if that's a perfect square, a perfect cube, if you think about what a power that's a cubed power means, that is a rational number. So we'll start that out. But a cube means a power of 3. So we're not just going to multiply by itself once. It's multiplied by itself twice. All right, so an example of that, you can get that down first. All right, Caden, give me a rational number, Caden. Keep it small. Do 6. So if I did 6, that's my rational number. And if I multiplied that by itself 2 more times, ultimately that means we have 3 of them. So a 6 times it, you give me a, hopefully I can do that. I think that's 216, hopefully. That 216 then is a perfect cube. All right, I think I actually have it down. Yeah, it is 216. All right, so that's our perfect square. That is our perfect cube. In this table, it is really, really helpful, and you'll still probably want your calculators as we move along through these problems to actually know what our perfect squares are. So all this is asking you is, if this is a perfect square, which it is, what number got multiplied by itself to give you a 1? And it would have had to have been a 1 times 1. All right. And then 4 is obviously then going to be a 2 times a 2. And then as we move our way down, these are all, for the most part, I would think through 100, we're pretty good with. So even if you don't fill all of these in, we should know these as perfect squares. This is a perfect square of 5. 36 is a perfect square of 6, 7, 8, 9, on and on and on and on and on. All right. So those are our perfect squares. So when I start simplifying these here in a moment, we start talking about perfect squares. These are the ones that we're talking about. Eventually, as you get bigger than 10, hopefully we're good with 11s to give you 121. If not, there you go. Hopefully we all know 12 times 12 is 144. Beyond that, things start getting a little sketchier. I won't make these too big when we start doing these problems in a moment. Oops. But those are our perfect squares. All right, up through 15. Perfect cubes, a little trickier, not as common, probably not something you've done a ton of, but it's the same process where if this is a perfect cube, and it is, the number that got multiplied 3 times is a 1. It's a 1 times a 1 times a 1 would give you a 1. And then these are all in order, so there's nothing to overthink here. 2 times 2 times 2 will give you an 8. That's why 8 is a perfect cube of 2. All right, we could also write these as like 2 cubed. All right, hence that's the reason it's called a perfect cube. The 27 is a result of 3 times 3, which would give you 9 initially. And then that 9 times the next 3 is a 27. So that's 3 cubed. That's why it's called a perfect cubed. All right. And then 64, that's a 4 times a 4 times a 4. All right. And then 125 is 5 times 5 times 5. And then 216. So now, the reason that is important, notice how it says up here that we want to take a cubed root. So don't change your table necessarily. But if I come over to this table over here, if I ask you to find the square root of 16, which you've done before, do we agree the square root of 16 is 4? Because that's what we squared to get a 16. Yeah, all right. So that's what we're doing. Like the square root of 49, you would get is a 7, because that's the number I squared to get a 49. When we come over here now, if I want a cubed root, if these are perfect cubes, cubes imply a power of 3. So you have a little bit of experience in this. You do this a little bit in Math 1. But if I now ask you to do the cubed root, that means I'm going to make that little index number of 3 there. That's asking you what number got multiplied by itself 3 times to get an 8. Well, the cubed root of 8 is a 2 because that's the number that got multiplied 3 times to give you that 8. If I ask you the cubed root of 64, you're looking for the number that multiplied by itself 3 times to get a 64. That would be a 4. So I would ask, if I said, what's the cube root of 64? You would tell me that is a 4. All right? Does that somewhat make sense? So keep that in mind as we go down here. All right, then we say the next little definition, the multiplication property of radicals. Radicals are square roots. So first, what a radical simply means, it's a square root. It's a cubed root. You've actually seen fourth roots a little bit back in your Math 1 days, but it's just a radical of some sort of a root. Well, if we're multiplying those, let's say I give you a square root and I have a times b underneath it. That means I could create 2 separate radicals, one with just a, one with just b, and multiply them together. Or let's use numbers, so it's a little more obvious. Let's say I gave you root 2 times a root 8. As long as those are both underneath the same root, so in this case, the square root, then I can actually multiply those together and get a square root of 16. And then this is one now that you've seen before. We actually know the square root of 16, right? What is the square root of 16? Armando? 4. So then that answer is a 4. So as long as they're both underneath the radicals, we can multiply them, or we can also kind of separate them. We can actually break them into their factors, which is what we'll do more times than not. All right. And then to simplify radicals, here's what you're writing for this. No perfect square, or cubed if it's a cubed root here in a minute, but right now we'll do a perfect square. So no perfect square can be left under the radical symbol. So the square root symbol, basically. All right, so here's what that now alludes to. Your directions here for these problems now is to fully simplify each radical, okay? So to simplify this, what we're talking about, we don't want to leave any perfect square underneath the radical. So this 75 itself is not a perfect square. However, think of ways that we could multiply to get a 75. And what we're looking for, since this is a square root right now, come up here and look at all of these perfect squares that we have to work with here. So think about if any of these guys go evenly into 75. So if we just consider our perfect squares, I think some of us would know this. Which one of the ones that I have highlighted in blue go nicely into a 75 evenly? Armando. Good. So what we're going to do is we're going to make one of those square roots a 25. And then how many times does it actually go into 75, Armando? 3. All right. So do we all agree 25 times 3 is going to give you 75? Yes. So this is our product property. If we multiply those together, we will get that 75. But what that now allows us to do, don't we know what the square root of 25 is? What is it? 5. So we're going to simplify this down to a 5. The square root of 3, if I go back to my list up here, is a 3 a perfect square? Is that one of our listed perfect squares? No. So there's nothing really we can do with that. So we're going to leave that as a root 3. All right. If you have your calculators, and I just realized I don't have mine up for whatever reason, I closed it out. Pull it out because you're going to use it anyway as these things get a little bit bigger. But what I want you to do, plug in root 75 into the calculator. So find that square root key first of all. And this thing takes forever to open. Here we go. Okay, so if I did the square root of 75, so if I'm not telling you to simplify, that's what it is a decimal. What we just said that was equivalent to is a 5 times the square root of 3, right? That's what we just simplified that down to be. So when I throw this into my calculator, it better give me that 8.6 again. All right, so when I hit enter, notice how it gives us that 8.6. All right, but that's us simplifying that. So we want to just break it down into its simplest terms. All right. All right, so the next one. If we, oops, wrong one, go to number 2, should be the nicest one that we do. 8 itself is not a perfect square, but if you look at your list of perfect squares that you have in the table on the left-hand side, the only one that would make any sense that goes into 8 is that 4, right? 4 times 2 is going to give you an 8. Then we know what the square root of 4 is. All right, Lily, what is the square root of 4? 2. So then we just write that as 2 root 2. That's our simplified expression for root 8. All right. All right, so number 3, before we add a wrinkle here in a minute, see if we're understanding those first couple. Do number 3. So if 27 can be broken down, is there a perfect square that we had in our column above that goes nicely into a 27? And if there is, you're going to break that up and then simplify whatever that perfect square would be. All right, and Ella, you got one? What is it? Okay, good. So the 9 is your perfect square. If you look at your column on the up at the top of the page on the left, so what I'm referring to is this column right here. These are your perfect squares. Ella's telling us the 9 is what goes into 27, right? And that is good. And then it would go into it 3 times. So 9 times 3 would give us 27, but since it's a radical 27, we leave the 9 and the 3 under that. And then what does the square root of 9 become then, Ella? Good. That just becomes a regular old 3. The root 3 is not a perfect square, so we just leave it. All right, good with that? Okay, so hopefully understanding those. Those are nice small numbers, not too bad. So now let's go to 4. See what you think for 4. Little bigger number, not quite as obvious. We want to look at our column of perfect squares and see if there is a perfect square that goes into 128. All right, here's where the calculator would become nice. All right, for a lot of people, these numbers you'll see, like number 6 is 405, so pretty large. All right, so see what you come up with here. You got it? Okay, just 1 minute. Here's the first one I call it. Okay. There's something that should happen here, and I want to see if you can catch it. Okay, Lily, because I like Lily a lot. Lily trusts me. But give me what you got, Lily. What'd you pick? Hold on. So stop there. So let's try that 16 and 8. If I go to my calculator and I do a 16 times an 8, Does that give us the 128 we were supposed to get? Yeah. All right. So in terms of what I've been telling you to do, go to your table, find a nice perfect square that goes into our number. Lily did that. She used that 16. All right. So if I come down to this number 4, what is then the square root of 16, Lily? Good. So that's then going to become a 4 and then a square root of 8. All right. So are we good with all that, right? That gave us the same thing. We took the square root of 16. That's going to give us a 4 root 8. All right. However, did you get yours corrected, Nora? All right. What did you pick, Nora? All right. 64 and what? All right. So she picked 64 and 2. So if I go to my calculator and I test 64 times 2, 64 times that 2 there, that's going to give me 128 as well, correct? So far so good. And then what did you ultimately find that 64 square root to be, Nora? 8. There's actually another one. Anybody have a different combo? I want to be bold. All right. Another one would be 4 and 32. All right. 4 goes in. If I multiply those out, I promise it's 128. That's going to give us a 2 root 32. So notice how there's really 3 legitimate things we have right here. All right. But here's what you want to be careful of with these guys. When we define these, what we said, no perfect square, or if it's a cube eventually on the back page, can be left underneath the radical. So if we go to these 3, so if we go to this one right here, the first one, if I look at root 8, can't root 8 be broken down a little bit more? Yeah, in fact, didn't we already do that right above it? Didn't we actually simplify root 8? So isn't there still a perfect square underneath that radical? And we can't do that. So if we did that, all right, so this was Lily's. If we did that, what we would just have to recognize is that this goes further. So I would now take the original 4, leave that out in front, and then I would take the 8 and do the same exact thing that we did up in number 2 and break that down. What that then gives us is what this 4 I'm going to leave alone. All right, and then Lily, what was the square root of 4 equal to? 2. So that becomes a 2, and then we leave that root 2. What is 4 times 2 going to give you? Go, Lily. So doesn't that give us this 8 root 2? All right. And then this is the one that doesn't leave a perfect square underneath your radical. So let me go to this one here real quick too. Our issue with this one is, couldn't I get 32 with a perfect square of 16 and 2? So that has a bigger perfect square that we could use. What that now gives us is not that. That would be a 2, and then the square root of 16 becomes a 4, and then a root 2. Notice how that settles in on 8 root 2 as well. So what you'll want to recognize, if you can go further, that means there is a bigger perfect square somewhere else that we would want to explore. But if you recognize that, you could also just go right from this step. This is ideally, this is the route we would go with if we knew that that 64 was the biggest, because then you can do it all in one step. But that won't always happen. Okay, so we want to recognize sometimes we can continue to go further. And then ultimately, all of these should give us this 8 root 2. Okay. All right. So 5. I think this is the last little trick here, and then we'll hopefully power through. See what you think for 5. Okay, I won't be cruel for too long. A lot of us are looking at the table, trying to think of a number, and now we're starting to plug into our calculator. Anybody coming up with a perfect square that goes into 30? No. There is, other than a 1, and if it's a 1, then it means you really can't do anything. So there are some times where we have a reasonably big number that can't be simplified. And if that's the case, you really can't do anything. Just to show that you don't skip it, so come an assignment, come a quiz or a test, and you're not just leaving it blank, you want to write something to the effect that this cannot be simplified. Let me know that you're aware of that versus just leaving it blank. But there's really nothing we can do with it. That's a completely simplified square root. Okay. All right. Do 6. This one can be simplified. All right. No tricks in this one. So see if you can come up with your number. And then depending on how good you are, here's really sort of the easiest route to take with these. If we know what our perfect squares are, so let me list them here. Not that. We really can just start taking this number and start dividing it by these. Do 405 divided by 4. If it goes in evenly, then it works. That one won't. And then go to your 9. See if 9 goes evenly into 405. It won't. So then we know that doesn't work. And we just start working our way down until we hopefully find one. Then you just have to be concerned about, is it the biggest one? All right, so could we go a little bit bigger maybe? Is there a bigger perfect square so we don't have to do multiple steps? Okay. All right, Jason, you got yours? Good. So 81 and 5, if you were to check that on the calculator, will multiply to be 405. And then what is the square root of 81, Jason? 9. So then we just do 9 root 5. And then root 5 can't be broken down any further, so then that's our final answer. All right. All right, 7 is the first one. We talked about it a little bit when we had to simplify it, where now I put a number in front. So this number, we're just going to drop down. That doesn't change. And what we look for are the numbers that give us an 18. All right, 18 is pretty straightforward, so we'll go ahead and do this together. 18 is 9 is our perfect square, and then that 9 times the 2 will give us the 18. Understand what's happening between all of these. These are all being multiplied together. So when I now simplify this, the 4 I'm going to drop down. It's going to get multiplied by this square root of 9. Joel, what is the square root of 9? So that becomes a 3. And then the root 2 we can't do anything with. So what we ultimately end up with in front of that square root of 2 is a 12, and then the root 2. So just 12 root 2. And we do need to simplify that down to this part. Okay? Okay, so number 2, same thing, or 8. Same thing, where that 2 is going to come down. All right, and then now try to find numbers that give you 80, with one of them being a perfect square. That factor chart would be good too, if you have that Mr. Kubowitz gave. If you have that factor chart, that would allow you to look at 80 and see what would multiply by itself to give you 80, if anything. Okay, anybody think they got a nice set of numbers for an 80, Julia? All right, she picked 16 and 5. Anybody find different ones? Okay, just to show it, just in case people are being shy and don't want to embarrass or feel like they're getting embarrassed. Wouldn't 4 and 20 also give you 80? And then isn't 4 a perfect square? So that sort of works, but what you would have to recognize, 20 is a somewhat big number, and 20 would be able to get broken down again. And if you know that, then start searching for a bigger number. And then that bigger number then, is 16. So ideally, we went with the 16 and 5 that Julia gave us. This then is 16 times, what is the square root of 16, Julia? 4. And then the root 5 you can't do anything with. So ultimately, we end up with an 8 in front and then square root of 5. All right, got all that? Okay, so now come the ones that make our head spin a little bit, because these are now perfect cubes. So what we're going to do, same idea, we're going to try to figure out two different numbers that multiply to be 250. Each of these radicals, though, should now have a little cubed root for that index number. So the little number inside is called the index number. So now they're cube roots. But now what we want to reference, if we go back to the front page, now we're concerned about, since there are cubed roots, now we're worried about these numbers. So now to get a 250, see if we can find a number that's a perfect cubed that will give you 250. So now these are our candidates. So now do 250 divided by 8, 250 divided by 27, until we find one that goes in nicely. Okay? So if we look at all of these, Jason, which one of these cube roots here, these are our candidates, go nicely into a 250? Good. So this 125 should go into 250 nicely. So if we go back to our problem now, we're going to take the cube root of 125, and it goes in how many times? 2 times. So 2 times 125 will give us the 250. But now we want it to be a cubed root. So let's go back to our table. What had we cubed in order to get a 125, Jason?
5.
Good. So that means if it's a bunch of 5s, that means the cube root of 25 is 5. So we come down here, cube root of 25 must be a 5. And then the cube root of 2 you can't do anything with, and then we leave that. All right, so those are cube roots. All right, so number 10. A little tricky here, right? If this is a square root, it's 9. The answer is 9. But putting that cubed root is a little bit different. So now what we're going to do, go to your table with perfect cubes, find a number in that table that is a factor of 81. Have you come up with it yet, Armando?
27.
Good. 27 is in that table, and 27 times what, Armando? 3. All right. So 27, and again, reason he chose 27, if I go to my cube roots, here is 27. And 27 is a perfect cubed of what number, Armando? 3. So that is why when we write it like that, if I ask you what is the cubed root of 27, you're going to put a 3, because it's asking what did we cube to get 27, and it would have been a 3. And then the other one just remains cubed root of 3. All right. All right. 11, just so we move along quickly. You're not going to find one. Again, 30 is not good. If we go through our candidates here, if you try to divide this by 8, that's a perfect cube of 2. That doesn't work. Your next one is a 27. There's nothing that happens. So 30 is also a problem for cube roots. So again, we would write something to the effect that this is already simplified, can't go any further. So don't waste too much time with that. But I want you to try one more at least here. Do 12. Because now we should be able to come up with a number from that list of perfect cubes that would give you a 40. Maybe we can do 40 and 41, hopefully. Okay, I saw Jason first. What do you think, Jason?
85.
Good. 8 was a perfect cubed of what, Jason? 2. So that becomes a 2, and then the cube root of 5 you're going to leave alone. All right. Okay, 13. Ooh, I don't even know what this one is off the top of my head, so I'm going to trust you guys. So cube root of 432. See if you can, hopefully there is one. I'm pretty sure I did have one. I don't think we would have given you this if there wasn't. Calculator's done. Who does? That is good. All right, good. All right, Mr. Krubitz, Cody. Mr. Krubitz said you were the first one he saw. What do you got?
216.
Good. And 2, right?
Yeah.
Okay. Yeah. The cube root of 216 and the cubed root of 2. Again, go to that list on the front page. What did we multiply itself 3 times with to get a 216?
6.
Good. So this here just becomes a 6. And then the cubed root of 2 is not a perfect cube, so you just leave that guy alone. All right. Okay, got a handle on this, hopefully. All right. Let me hand this out. Okay, you do have some homework. Mr. Kubitz will give you this. While you're doing that, again, any of those retakes. So I think I had 3 or 4. Ms. Kubitz had 1 or 2 last Friday. There are intervention days this week, actually Tuesday, Thursday, and Friday. So if you're planning to try to take an opportunity to retake that test, you need to see us one of those 3 days. And then we get you scheduled. If you do it tomorrow, then we can get you to do the test on Thursday. If you do it Thursday, we can have you take it on Friday. But any opportunity, you need to see us before Friday for that opportunity to take place. What I want to tell you is when you sign up, if you sign up for me, just because my co-teacher gets mad at me for this, and I've already talked to my calc kids, I forgot to tell you guys. When you sign up for me, there is 2 of mine on there. Sign up for the one that is just my name. All right. There's another one that has my name and Miss Walker. That's her class. She doesn't have her own class for whatever reason. So if you sign up, don't sign up for the one that says me and Miss Walker. Just sign up for the one that has my last name. Okay. Otherwise, I get in trouble on the home front during my advisory when people are signing up for that one. Okay. It's kind of like being married. You don't want to get in the doghouse because it's hard to get out. Right. So get signed up before Friday if you're planning to try and retake that test, okay? And so we had a test, or we had a big assignment in class due on Friday, and we had a test today. And then I had a bunch of people wanting to come in, so there were like 5 people signed up for her. And I'd already talked to a few of these people that signed up for that one, understandably. Yeah. Hello, I saw you on Twitter.